Hi, this is Shawn Gao from MTS. Together with Dr. Huang at the University of Toronto, today we are going to run some demo tests to show you how to use Nikon to perform hybrid simulation. Nikon is a program developed by University of Toronto, and it can talk directly with MTS control software through the API we provided. So the physical test substructure today is that biaxial test rig you can see there. It has one column being physically tested. The numerical substructure we are going to run today is this one showing on my screen, which is basically a one-bay, one-story frame structure. And you can see one column is missing because that's going to be physically represented in the lab. We will run several tests today, each time with a different modeling package running the hybrid simulation. We will also be running some distributed hybrid simulation where the test, again, is in the MTS lab in Minnesota, but the models will be running across the country line at Toronto in Canada. So now we will start our first demo test. So this one will be running an OpenSees model as a numerical substructure, and it will be all running locally here at my MTS PC. So I'm showing my screen here. We have a MTS 793 software now started. Now I'm going to just start hydraulics. And then turn the HSM to high. I'm going to bring the actuators back to the zero load position, just to make the initial condition right. And there is some offset. I'm going to auto offset that. So now basically the actuator is back at zero load and zero displacement. So the physical test is ready. The next step, I'm going to start the Nikon program. Again, that's the program developed by University of Toronto. Dr. Huang and Dr. Huang, they are showing here their name. So Xu, do you want to introduce Nikon a little bit to us?
Sure. Hello everyone. My name is Huang. So right now I'm Postdoctoral Fellow at the University of Toronto. So as for the Nikon programs, after we click the button, like to run the programs, it shows some basic information. So, for example, it's developed at the University of Toronto and also the release date. So if we're ready, then we can just press enter to continue. Yeah. So after we press the enter button, the programs will read two configuration files. The first configuration file is called Nikon.cfg file. So this file deals with the very general descriptions about the test setup. For example, it includes the number of control points and the number of control degree freedoms. For this simple test, because we only have one control node, and we will control the two translational degree freedom. So as you can see, the control point number is 1, and the control degree freedom is 2. As for the output signal, which means that the measured displacement and the force together, so it should be 4. So, and also it includes the parameters about the ramp time and hold time, because in current development of the Nikon programs, we are using the ramp and hold scheme to impose the displace command to the test setup. So then if everything looks great, then we can press enter again. Yeah. So after that, the program will load another configuration file. So this configuration file deals more with the coordinate transformations. As we know that the programs from the OpenSees will send the displacement command in global coordinate system, which are not consistent with the actual strokes or testing setup that we're using in the lab. So in this case, we need to specify the locations of the actuators such that the received displacement from OpenSees can be properly transferred into the actuator scopes. So if everything looks great, then it's good time to press enter to proceed to the next step. Yeah, after that, as you can see, the Nikon programs shows the message waiting for connections. So now we need to run the OpenSees model to establish the communication for that exchange.
Okay, so now I'm going to start OpenSees. So I started OpenSees here, and then I'm going to run the model. And the name of the main file is this frame 1 by 1 by 1. And then I start enter, I hit enter. As you can see here now, Nikon has some check to do. Xu, can you introduce about this function a little bit too?
Sure. After you press the enter button, then you can see some message saying that the connection has been successfully established. So which means that the OpenSees has been successfully connected with the current Nikon programs. So after that, when we press enter again,
yep.
Yeah, then Nikons will read the current displacement and force measured from the test setup. So that's just the initial positions of the actuators. Then if it looks great, for example, if all the this measured force and displacement are close to 0, we are good to go. Then we just press enter again to start the real simulation.
Okay, so that's the last step. I'm going to start it right away. Now the test has started. And as you can see, both on the Nikon as well as on the OpenSees, it's starting to show, the steps it's running. In the meanwhile, you can see the test started, the rig is moving. There is animation showing on the left bottom corner of my screen, showing how the numerical substructure is moving. And that, again, the boundary condition is enforced at that interface node. So basically, that numerical substructure is synchronized with the physical test substructure to perform the entire hybrid simulation. So we have defined to run 500 steps of El Centro earthquake as the input excitation. So the 793 on the top window here, I'm showing the command, displacement command for both X and Y actuator. And on the bottom scope here, I'm showing the force and displacement feedback for both actuators. So there are 4 signals altogether. So the test will progress. Now we are at the step number 400 something. So at 500, then it will stop. Okay, as you can see now here, at the step number 500, as we defined, it finished the hybrid simulation, and Nikon basically has a display message showing the communication is done, and now we can stop it. So now we are going to run the second test. This time we'll be running an Abaqus model instead of OpenSees model. And this time we'll be running a distributed hybrid test, meaning that the model will be running at the University of Toronto site. So at MTS here, I made sure the MTS test station is ready, the hydraulic is on, the actuators are back at 0 load, 0 displacement. So what I need to do is I just need to launch the Nikon program like I did last time. and then make sure Nikon is ready to wait for the connection. Now I'm going to let Dr. Huang explain the model and start the test.
Okay, so now let's consider the same 1 by 1 by 1 frame structure. Similarly, one of the columns will be tested in the MTS lab in Minnesota, and the rest of structure components will be numerically modeled. But this time, the numerical portion of these structures is included in this Abaqus model running on a computer at the University of Toronto in Toronto. The interface program Nikon is still used to establish the communication between this Abaqus model in Toronto and the physical specimen in Minnesota. So now if we look at the detailed Abaqus input file as shown here, so we have a structure node specified here, and then we have the different elements for the bins and the columns. Also, we have lumped mass specified at the top 4 nodes of the frame structures. And here we have detailed modeling of the sectional geometry and the material properties. So now, to enable the communication between this Abaqus model and the Nikon programs, we need to include a user-defined subroutine as shown here. From here, we can specify how many interface nodes do we have and how many degree freedoms will be used for data exchange. And here also, we have the port number specified for TCP/IP communication. And beyond that, it's quite similar to any other standalone Abaqus model. So here we also have the boundary condition and also the ground motions to be applied along the X and Y directions. So now, because the test PC is ready, so we can run this numerical models from a command window like this. So now, firstly, we input Abaqus to launch the Abaqus software, and then we have this model job file IM, and also we need to link with the subroutine that I just mentioned. So if everything is ready, then we can just press enter and start the simulation. So firstly, the Abaqus will check the license and also do some error checking, and after that, it will launch the main solver to do the numerical modeling. So now, as you can see, the connection between this Abaqus model and the Nikon has been successfully established. So now we can go back to the test PC, and Shawn from there can just press enter to proceed the simulation.
Yes, I saw it on my screen here. The connection is being established. So then I can go ahead and let the communication start. And then it does again some initial checks on the feedback signals, just so that make sure your feedback is not at a large value. Now everything is ready. I'm going to start.
Okay, good. As you can see, yeah. So here are the Abaqus models. So just showing the number of steps has been completed.
Yeah, this is what you can see on the test PC. Basically, Nikon allows the Abaqus model to be connected in remotely, and they started the hybrid simulation. And if you want to take a look at the command and feedback side, this is what the actuator is doing. So because Abaqus is using a implicit solver here, it takes 3 iterations for each time step. That's why you can see there the step, every time step it has 3 iterations, right?
Right. So it may take a longer time than the OpenSees model, because in the previous OpenSees model, we are using the alpha-weight schemes without any iterations for each time step analysis.
So as you can see here, at the end of time step 500, the communication is done, the hybrid simulation is finished. So now Xu can show you some post-process from his PC.
So the Abaqus has a very well user-friendly post-processor. So from here we can briefly review the deformed shape during the earthquake. And also, we can also plot the displacement history of the structures for a specific structure node. So for example, here I am going to plot the displacement at this node, which is also the node to control the physical specimen. And we just save. Okay, so from here we can plot the displacement history of this node along the x direction. So here shows the displacement history. So that's the end of the demo test for Abaqus.
So now we are going to run the third model, which is in MatLab. Again, this time will be distributed. Toronto will run the model. Again, I have all my tests ready. I have Nikon started here. I will just give Nikon the connection is waiting now for the Toronto side.
For the purpose of illustration, here I have a MATLAB script for modeling the same 1 by 1 by 1 frame structure. As you can see from this script, it starts with the loading of data exchange library, which is the key of the UTSIM framework to enable communication between different programs. Within this library, we define a standardized data exchange format as well as several functions to transfer data in a seamless manner. After that, I also specified the port number as well as the IP address of the test PC. And then it calls the setup connection functions within the data exchange library to establish communication between this MATLAB script and the remote Nikon program. Also, I included the functions to define the elemental stiffness matrix of the beams and the columns based on the geometry and the material properties as specified here. In addition, it also includes the functions to obtain the global stiffness matrix. And here I also defined the mass matrix and the ground motion along the x and the y directions are loaded in this MATLAB script as shown here. Besides, I also specified the damping matrix based on the mass and the stiffness matrix that I previously defined. And then I include a for loop to go over all the analysis steps in this simulation. And in each analysis step, it involves the calculation of the trial displacement of the system, and it will be sent to the remote Nikon programs using the send data command within this data exchange library. And once the force is measured, then it uses the receive data functions within the same library to obtain the measured force of the test specimen. And this measured force will be used to update the acceleration, velocity, and displacement of the system. And these steps will be repeated until the end of the ground motion. And once the simulation is completed, it uses the terminate functions within the data exchange library to close the communication between this MATLAB script and the Nikon program. And finally, the predicted displacement history of this system will be plotted. And in this demonstration, the MATLAB script will be running on a simulation PC in Toronto, where the physical specimen will be tested in the MTS lab in the United States. And once the MTS 793 and the NICON programs on the test PC are ready, we can start a hybrid simulation by running this MATLAB script. And from the command window, we can track the status or progress of the simulation.
Yes, from the test PC side, you can also see that Nikon now started to receive command from Toronto, and the test has just started. Okay, now the MATLAB model is completed, the hybrid simulation is finished, and the program aborted properly. So this is really to show you that you can use a variety of different modeling software to perform hybrid simulation utilizing NICON and MTS software. Okay, now we are going to run the last test for today's demo. This time will be basically the same model, but built by Python. And the same story, I have the test already, the Nikon is started. I will make the connection ready for connect.
Similar to the MATLAB script that I just explained, I also developed a equivalent Python code for running the hybrid simulation. So this is the Python code that I made for the same 1x1x1 frame structure. Similarly, it also started with loading the data exchange library, and then it lists the functions implemented in this data exchange library. And here I need to specify the port number and IP address of the test PC. And again, it used the setup connection functions to initialize the communication between this Python script and the remote NICON program. And also I have these functions to define the elemental stiffness matrix for the beans and the columns. And here this is the functions to obtain the global stiffness matrix of the system. And here I have the mass matrix defined, and also the ground motions along the x and the y directions. And in each analysis step, it always calculated the troy displacement, and then send the troy displacement using this send data function to the NICON program. And after the measured force is available, it used the receive data function, as shown here, to obtain the measured force. And then the measured force can be used to update the structural response. And at the end of the simulation, it used the terminate functions within the library to close the communication between this Python code and the remote NICON programs. And once the test PC is ready, we can run this Python code to start a hybrid simulation.
Okay, the simulation is done. So we're finishing all the demonstration tasks. So in this presentations, we briefly shows the development of the ETSIM framework and how to use it with the MTS for hybrid simulation. And in this test, we try the open source software OpenSees And also we tried the commercial finite element software Abaqus. And also I user-defined programs in MATLAB or Python can also be used to run hybrid simulation with MTS.